The equilibrium constant. Although we can investigate the rates of reaction by looking at the concentration of products or reactants as a function of time, this gives us little information about the extent of the reaction. We can define, for any reaction, a reaction quotient Q, which gives a numerical value for the extent of a reaction. This is defined as the ratio of the concentration of the products to the concentration of the reactants, raised to the power of any coefficient contained in the chemical reaction. For example, the reaction A plus 2B going to the product C would have a reaction quotient of C divided by A, B to the power of 2. If the reaction quotient is large, this means a large amount of product in the system, and the reaction has proceeded to the point where the major species is the product and the minor species is the reactant. If the reaction quotient is small, this indicates there's a lot of reactant and very little product. So the major component is the reactant and the minor component is the product. When the reaction quotient is equal to the equilibrium constant for that reaction, the system is defined to be at equilibrium. So it's easy to see that you can use this reaction quotient to find out whether a reaction has reached equilibrium or not. If Q is less than K, then there's more reactant than product, and the reaction is incomplete and must proceed in the forwards direction until Q is equal to K. If Q is greater than K, then there's more product than reactant, and the reaction has gone past equilibrium and must proceed in the reverse direction until Q is equal to K and equilibrium is re-established. Q can be worked out from graphs. If we plot the concentration of the reactants and products as a function of time, then the reaction quotient can be calculated at any point in time. At equilibrium, obviously, the reaction quotient is equal to the equilibrium constant, but before equilibrium, Q is less than K, and after, Q is greater than K. So we have an example here of carbon monoxide plus chlorine gas, which produces carbon oxychloride or phosgene gas. And we're going to look at the reaction quotient at various times. At T equals 0, the reaction quotient is the concentration of carbon oxychloride divided by the carbon monoxide and chlorine concentrations. We're going to read these off the graph. So it's about 1.7 divided by 0.7 and 1.1 for each of those concentrations. And this gives us a fraction of about 2.2. At time of about 3, so a little bit further along our concentration time graph, we have a different reaction quotient. We read this again off the graph, and we get 2 divided by 0.85 times 0.5, and it gives us a value of about 4.7, so it's slightly higher. At T equals 10, which is well into our equilibrium region, we can read off the values from the graph, and we get a reaction quotient which is 10, which is equivalent to our equilibrium constant.